Good evening, students. Krushi sir again bringing a very important discussion today for you. This is based on the RC value of an RC circuit, the time constant. Basically, we call that RC value. Okay, it's a very typical question, and based on these questions have been asked in J Advanced especially, and can be asked in J Mains also. Is not a big issue. Okay, what is the question? A capacitor is made of two arbitrarily shaped conducting bodies. Two conducting bodies, shapes are arbitrary. They are immersed in a vast expanse of very poorly conducting homogeneous dielectric medium. Call it medium, material, medium. Call it medium. Okay. So, two arbitrarily set conducting bodies immersed in a vast expanse. This is very important also, note it. Vast expanse of a very poorly conducting, poorly conducting means resistivity very high, not infinite, but very high. There is nothing where the resistivity infinite. So, poorly conducting homogeneous dielectric medium having a dielectric constant K. Dielectric constant is K. Okay. The separation between them is large compared to their dimensions. What is the time constant of this capacitor? Okay, resistivity of the medium is rho is very high. So I have drawn this. The whole space is a very vast expanse of dielectric medium, but poorly conducting. Means some conduction can take place, maybe very less, but still not zero. So current can, a very minuscule current can flow. If I maintain a potential difference V between them, a minuscule current can flow. I won't say current is zero. And I've shown you the lines, the field lines. K is the dielectric constant, rho is the resistivity. I've shown in a schematic diagram these lines of forces almost being perpendicular to the surface of the conducting bodies. These are the conducting bodies. Conductors 1 and 2 are given. These are conductor. This is also the conductor. Okay, they have given the 1 and this is 2. They are giving charges Q and minus Q respectively, as you can see. They are immersed in a large and a very poorly conducting dielectric medium. This whole thing, that space is a very poorly conducting dielectric medium, very large, having resistivity rho, which value is very large, and dielectric constant K. For conductors, rho is very small, orders of 10 to the minus 6. But for poorly conducting, the rho value can be order of 10 to the power plus 6, plus 7, plus 8, whatever may. Electric field lines are shown in the diagram, just arbitrarily are shown there. And since it is very poorly conducting, current flow is insignificant, so the field lines will almost be normal to the surface of the conductors here. That's what I explicitly written. Field lines are shown in diagram. Since the medium is not a perfect insulator, a minuscule current flows from 1 to 2. We call it leakage current, and we call this leakage capacitor as well. Leakage capacitor. Questions have been asked based on this. I'm not giving something very out of place. Okay. Here I have written the very crucial point. Since the current flow is negligibly small, the electric field lines will almost be normal to the surface of the conductors. That is very important. Then I have drawn a Gaussian surface. You see this red line here, enclosing the surface of the conductor 1, just outside the surface of the conductor, but lying in the dielectric medium. I understand this Gaussian surface. This Gaussian surface which I am showing you, this is the Gaussian surface. let me write it. Gaussian surface. Are you able to see this? Thus close to the boundary of the conductor. Okay, so this is what I have drawn here. So I am applying the Gauss law here. How to write the Gauss law when the Gaussian surface passes through a conducting in a dielectric material? Okay, there is no change in Gauss law. Actually, always I can write E dot dA integration or a closed surface is Q enclosed by epsilon 0. But in case the surface is a dielectric medium through which the medium is the space is a dielectric medium through which the Gaussian surface passes, this Q enclosed will include the free charge as well as the bound charge. Bound charge means charge due to polarization. Free charge means any charge which is not due to polarization, like I give some charge, battery supplies some charge. These are the free charges. And bound charge means the charge which is due to polarization. You can refer to my discussion on this in December 15th. The topics in the important discussion on the electrostatics, lecture 1. You can see that. What is free charge, bound charge? So include the free charge means the charge which is not due to polarization, and bound charge is the polarization charge. So both has to be enclosed, included in this Q enclosed. But if I want to write only the free charge, which I have been doing so far using Gauss law, then what should I do? I write the Gauss law like this: Ke dot dA integration. Okay. Later we call it in higher class, we will call it displacement vector. Then do forget about it. So Ke dot dA integration, K is dielectric constant. Ke dot dA integration, I am taking it a homogeneous medium, so K is same throughout, is equal to free charge enclosed by epsilon 0. Very important. Q is the free charge, only free charge. There is no trace of any bound charge or the polarization charge which will appear due to polarization process in the dielectric medium, which is at the neighborhood of the surface of the conductor. That we don't include that bound charge. We need not, because if we write Ke dot dA integration, this is a crucial part. This is also a note I wrote. If I write only E dot dA integration, that Q enclosed by epsilon 0, Q enclosed must include free charge and bound charge enclosed within the boundary of the Gaussian surface. By writing Ke dot dA integration, then we write only Q free enclosed by epsilon 0. We take only enclosed free charges. The free charges are all charges which are not due to polarization. That's all. You can embed some outside charge, or you can give some charge. Battery can supply some charge. All these are free charges. Now to find the current flowing from, so this equation I wrote, Ke dot dA integration, this capital Q, which is the free charge only, by epsilon 0. Capital Q we have given to the conductor 1, and minus Q I have given to the conductor 2. You have any in a battery must have given actually. I don't have any capability to pick up charge and place there. I must have used a battery to do my job. Okay. So now to find the current flowing from conductor 1 to conductor 2, what should I do? What should I do? Same in that Gaussian surface or that closed surface we consider. If the the current density J bar, so J bar dot dA, if I integrate, I'll find the total current coming out through the closed surface. That's what I wrote. J bar dot dA integration over that closed surface, that same closed surface, same enclosed boundary, is equal to total current I, where J is the current density at each point of the closed boundary, and I is the total current flowing from 1 to 2. But we know that J bar is sigma E bar. You must be knowing this. In a homogeneous medium, sigma is same throughout. So J bar is equal to sigma E bar, but sigma is 1 by resistivity, so 1 by rho E bar at any point in a medium. So therefore, equation 2, how can I write? E bar by rho, that is J dot dA integration is I. So rho you take to right hand side. So E dot dA integration over the closed surface is rho I. But from equation 1, K dot d, if I bring K outside, what should I get from equation 1? K I took outside and brought to the right. So E dot dA integration closed surface will be Q by K epsilon 0. So plus 3, 4 you compare. 3 is E dot dA integration closed surface is rho I. Similarly, E dot dA integration close over the closed surface is capital Q by K epsilon 0. That is from the Gauss law. This is from the basic definition of the current and the current density. So equating both E dot dA of the equation 3 and 4 together, I get rho I is equal to Q by K epsilon. Or Q by I is how much? Rho K epsilon 0. Mark it. Because equation of 5 very, very important. Okay, let V the potential difference between the two conductors. So I have shown you in the diagram. This potential difference you have maintained as V between them. When the charge is capital Q minus Q, the potential difference is V. That's what I am saying. And here I am writing that. If let V the potential difference between the two conductors, C is the capacitance of the given geometry with the given dielectric medium, and R be the resistance of the poorly conducting path between the two conductors for the particular geometry of charge flow. How the charge is flowing, that I do not know, but for that geometry, whatever the resistance, that is I call it capital R. Okay, capital R. So C capital R. Okay, this is what I am giving. So that means Q must be C into V and capital I must be V by R. These two we know. So this Q by I ratio, if I want to write CV by VR ratio. So Q by I will be how much? VB cancel, so RC. So Q by R is Q by I is RC. And looking at the equation 5, this Q by is RC, RC is rho K epsilon. Okay, RC is rho K epsilon 0. लिख देते हैं इक्वेशन 6 करके. That's what we found. एक एग्जाम्पल देता हूं, आप लोग तो खुश हो जाएंगे आप. एक एग्जाम्पल देख लो. If the given conductors in the diagram are spherical, they are spherical only, having radii A and B respectively and separated by a distance d which is much larger than A and B. Find the resistance between them if we maintain a potential difference between them. So the potential difference मैंने maintain किया, I maintain potential V between them. So जो resistance इनके बीच में किस है, कुछ तो current flow करेगा ना, same poorly conducting. So what is that resistance between A and B? So first we will calculate the capacitance between the two conducting spheres. We know that from basics of capacitance between two conducting spheres separated by large distance, the capacitance is 4 pi epsilon 0 AB by A plus B. If the surrounded by a vast expanse of dielectric medium, then K will become epsilon 0 will be K epsilon 0. So is how much? What is the C value? C value is 4 pi K epsilon 0 AB by A plus B. You must be knowing this. Otherwise, you refresh your knowledge or your whatever you learned about capacitor. Just refresh that. Using this in equation 5. Equation 5 में क्या है? RC value है ना भाई. C मालूम हो गया तो R तो मालूम हो जाएगा आराम से. So rho K epsilon by C. That's what I am saying. Now you must be understood. Rho K epsilon by C. So rho K epsilon 0 divided by this value. So इसमें K epsilon अब cancel हो जाएंगे. So what will get? Rho into A plus B by 4 pi AB. This is resistance. This will be the resistance. Okay? That's it. And the time constant of this rho K epsilon that you already we have found out. कुछ numerical value देखते हैं. Let's say rho is very poorly conducting, very high resistivity. 1.13 into 10 to the power 6 ohm meter. 1.13 मैंने क्यों लिया? कैलकुलेशन इजी करने के लिए. K is 10. Epsilon naught 8.85 10 to the power minus 2. This is SI units, Coulomb square by Newton meter square. This ohm meter is a number. So rho K epsilon 0 से multiply कर दो, ये 1.13 8.85 multiply almost 10 हो जाएगा. So this 10, K is 10, so 100 into 10 to the power 8. How much it is coming? 10 to the power 6 हो रहा ना. 100 rho K epsilon 0 10 to the power minus 2 सेकेंड आ रहा है क्या? तो 8 कर देता हूँ. चलो उसको मैं 8 कर देता हूँ. 8 करता हूँ. मल्टीप्लाई करो. इसको मैं 8 कर देता हूँ. That's the numerical application of this. So 1.13 into 8.85 is 10. 10 into 10, 100. 100 into 10 to the power 8 into 10 to the power minus 12. So that is 10 to the power minus 2 seconds. So just to match my answer, I change it to this. This is such a big yeah. Okay. So this is the RC value. Then how much it is the C value? C value is 4 pi epsilon 0 K AB by A plus B. Is that correct? 4 pi epsilon 0 1 by 9 into 10 to the power 9. K is 10. I'm taking A as 5 centimeter, B as 2 centimeter radius. So 5 into 2 into 10 to the minus 4 and 5 plus 2 7 into 10 to the minus 2. So this will become how much? 16 picofarad almost, because 10 goes to this 2, so this cancel out. So 10 to the minus 9, 1 by 16, 1 by 63 is almost 0.16. So 16 picofarad. That's correct on. Okay. So what is R then? Whatever RC value I found, 10 to the minus 2 divided by C. C is how much? 16 picofarad. So this you can 10 to the power 10 by 16, 0.06 10 to the power 10 or 0.6 gigaohm. Quite a big resistance. 0.6 gigaohm is the resistance between these two, and when separation is large between them, and the capacitance is, as I told, what the value of capacitance? Picofarad, 16 picofarad, and RC value is 10 millisecond. Okay, close. You see, these are not exact values. If I multiply, I get 10 millisecond. Okay, that's it. Understood this? So इसमें नोट में अगर एक क्वेश्चन पूछा था एक बार जेई एडवांस में, different geometry दिया था. So if initial potential between the spheres is V naught, then V at any time, t, what is the potential? V naught e to the power minus t by tau. This you can write always. Must be knowing the basics of RC circuit. मैंने इसे रिफ्रेश नोट लिख दिया. by refresh कर लो. आपका जो for calculation of capacitance between two conducting spheres separated by large distance. Is it okay? It's a quite useful discussion for you. It will help you because these questions have been asked already, this type of question. So now you are in a position that in this condition, RC value is rho K epsilon 0, irrespective of the geometry. I did not check any geometry. I took arbitrary shaped conductors. So people have proven by taking two parallel plates having a couple. That is a very special case. But this way we have proven for a general situation. Okay. So this is very important for you. I hope you enjoyed my lecture today, and you must have you understood. Then you must remember this relationship, and now you can apply it very easily. Is it okay? And know that it's a leakage capacitor. I can replace it by a ideal capacitor. This I can replace this like this. An ideal capacitor having a dielectric and having a large resistance here. Okay, this is equivalent to that. Am I clear? It's a leakage capacitor discharging. I can see because battery is not connected anymore. Battery is initially connected, then disconnected. Then after that, you will automatically discharge. And all the capacitors reality are the leakage capacitors only. Because the surrounding space air is there, it will have some kind of conductivity. Understood this? However small conductivity may be, but it has not zero. Right? So all of you have understood our discussion. All the best for your exam in this ensuing exam, whatever you are going to write. Do well, be confident, don't take unnecessary pressure, just throw the pressure to dustbin. Enjoy whatever you know, answer correctly, confidently, you will do well. All the best for you. Thank you all. We'll discuss again with a new important topic. Thank you all.